about a few quick concepts that we're just going to address, but we're not going to kind of get into real detailed kind of analysis of it because it's an entire branch of mathematics. We're talking about graphing these polar graphs, okay, and some things that we can do with them. All right, so I believe on last time we met, we graphed something that looked like r equals 2 plus 2. I think we did sine theta. Okay, 2 plus 2 sine theta. So it looks something like, let's see here. The way we did that is kind of the long way. And this is the argument of, outside the scope of this course. We're not going to get into this. That is a family of curves, 2 plus 2 sine theta. And as those 2's change to 3's and the 4's, we can recognize what that does to the graph and say, okay, what are some shortcut techniques that allow us to get this graph much quicker than running through a 2-column kind of input-output procedure. Does that make sense? All right. But that's what we did on Friday is we chose thetas going from, pi over 6 all the way through, I think we went to 2 pi. And then see what are the R values that we generate when we evaluate at those different thetas. And then gave us like 16, 17 points. We plot those points. Okay. And then look at the curve that was generated. And the curve that was generated looked like this. R equals 2 plus 2 sine theta. Okay. Now, to be honest, I don't use polar graphs a lot. I don't deal with these a lot, so I'm not 100% sure and extremely confident in the way I graph things in GeoGebra right now. I'm fairly so you see how it puts it as a parametric curve. It doesn't say it's polar, it's parametric, meaning that it's still graphing it in regards to, like, in the background, x's and y's, but in parametric it means in respect to a third variable, usually time. But this is our 2 plus 2 sine theta. That is a polar curve there. And if we put the polar grid in the background, it does match up to what we came up with by hand the other day. Okay. And I asked you guys what that looked like, and you said a butt. Okay. Did I say that? Oh, I tried to get you to say that. Okay. But that is a cardioid. Okay, it looks like a heart, right? Okay. The only thing that happens when I change the sine to a cosine is that when I change 2 plus 2 cosine theta, now it's going to be symmetric about the x-axis instead of the y-axis. Okay. And a lot of the curves that we deal with, if it's got a cosine on it, it's usually going to be somehow impacted by the x-axis. And if it has a sine on it, there's going to be some relationship with the y-axis. So that is a cardioid. Now, the thing that has to happen is that these numbers, I'm just going to put A in here right now. Let's see here. Well, it doesn't know what A is right now, so let's see here. All right, so if I just graph R equals A times sine, sorry, A plus A sine of theta. See, this is my issue sometimes with this. Well, I apologize. I was trying to get to do this. So let's go r equals 3 plus 3 cosine theta. What in the world? Let me just restart GeoGebra. Huh? Desmo. I'm not familiar with Desmo's way of kind of creating sliders and stuff like that. Let me try it. If I go r equals let's say a plus a cosine. I'm gonna throw theta in there, so you know where theta is on this thing. Oh, good call. All right, so you see, there's our cardioid. I mean, it does a decent job. But as I change that A, what's the only thing that it does? Just changes the size, right? Okay. So what that looks like right now, guys, what that is like 3 plus 3 cosine. It's where this number here and that number there are identical. Okay. And that generates that cardioid. Now, if I make these different, maybe I put a B here. Back. B. Okay. Don't like how I did that. There you go. So now they're the same. So it's still cardioid. So it's still 1 plus 1 cosine. But now if I make that number get bigger, it starts to look more circular, right? Okay. But it's not a circle. Okay. We'll kind of talk about this as we move on. But let's look at what happens when I make that 2.3. Let's make the B value bigger. Starting to look like a cardioid, right? And now it is a cardioid. But let's make that B value go even larger. And it starts to loop on itself, right? Okay. This is referred to as a... I always spell this wrong, so give me a second. Okay. It's called a limousin. I think that's how you pronounce it. I'm not sure what that little symbol and the C, how you're supposed to, the phonetic way of pronouncing that. But that is Latin, or comes from the Latin word snail. Okay. I don't know why they think that. All the polagraphs kind of are named after what they look like. I don't know what a snail. I don't know what aspect of a snail that looks like, but that is a limousin. Okay. And as we move that number bigger and bigger, that loop gets bigger and bigger. Okay. Now this is the reason why on Friday I talked about how when you plot points for these things, once you plot 2 points, you want to connect them. Okay. And you plot your third point, then you connect it, and you plot your fourth point, you connect it, instead of plotting them all at once and then connecting all at once, because you lose sight of the order that they're plotted, and you'll miss out how this loop is supposed to be graphed. Does that make sense? Okay. So you'd like plot that point, come up here, plot that point, maybe that one, and you, as you go, you're going to go and conduct that loop, and then come back through and finish off. Okay. There are some others that I'll show you. There's something called a limnoscate, I think is how you pronounce it. Let's go R equals A squared. I mean, important person. Cosine 2 theta. Okay, so that looks pretty cool, but that's not what we're looking for. Okay. That is a limnoscate. Okay, it looks like the infinity symbol, right? If I change it to a sine instead of cosine, it just does that. Okay. Let's see what happens when I change that to a. Okay, so I changed it to 3, looks like that. Change it to 4, looks like that. Change it to 5, it looks like that, right? Okay. So these things kind of look interesting. If I manipulate the A, all the A does is change the size of it. Okay, so it's kind of like a scalar multiplier. The one thing I want you guys to understand is that this is a fairly simple looking expression. Would you guys agree with that? Even though it's somewhat complicated, but fairly simple. If I were to put this into X's and Y's, that thing is going to be a mess. Okay? And that ends up being the benefit of having a polar graphing kind of side of things, is that it creates or allows us to work with equations as a simpler kind of version.
What would have happened if you made the value next to theta like decimal?
Might not know what to do. Does that? And that's the thing, is that that's what I'm talking about outside the scope of this class, is that that's a family of curves, right? So we could spend, like an entire semester, maybe even an entire year, trying to investigate what are all the relationships that exist when we start altering these numbers. Okay. If I take, instead of basically I'm taking square root here. What if I take the 4th root? What happens there? Okay. What if I don't take a root? Doesn't know, I guess. There we go. So I get something that looks like that. Okay. So all families of curves, and we're going to start to see that as we change, we start to get different things. Maybe I multiply this. Let's see if I multiply by b, what does that do? Okay. Or multiply by, let's say, cosine of theta times b. And you start to get some pretty weird, intricate, but very symmetric curves a lot of times, right? Okay. That in terms of x's and y's is going to be a mess. Okay. So that's a lemniscate. We've got something, it's actually a pretty easy one. It's called Archimedes spiral. And Archimedes spiral, let's move this a to a smaller value. Okay. Archimedes spiral. Now I got a kind of a very small negative value here for A. But as I change that A, you start to see that spiral just kind of gets. It kind of makes sense? All right. Show you some that are very common, pretty easy formulas. Now changing into x's and y's is a pain in the butt, but r equals a times cosine. Let's just go b theta. Okay, so a, I'll just make 2 in this case. Get back to a standard view. All right, and I want b. All right, so this is referred to as a rose. Okay, and what I've got here is just it'd be 2 cosine of 2 theta. All this 2 up front does is change the size of it, right? Okay. But this 2 here, now I'm going to try to focus on just using integers here, which is one of the things I don't like about Desmos, is that I don't think I can force it to use just integers, unless you guys know how. But if I change it to a 3, you see that happens, right? Okay. 2, I have 4 petals. 3, I have 3 petals. 4, I have 8 pedals, right? But 5, I'm going back to 5 pedals. Okay. So what happens here is that if I have just some number out front, I don't care what it is, call it A, cosine of, let's just say n theta. If n is even, you have 2n, we'll call them pedals, okay? If n is odd, you have n pedals, okay? And then you saw as n was like, as n becomes a fraction, okay, or a decimal component to it, you start to get those types of things, right? Okay. Another family of graphs. You guys forget what they're called. They used to come in when I was little, like a little case, and they had little plastic rings, and you put your pen in it. They're little circles, and you move your pen in circles, and it created an image. You guys know what I'm talking about? Spider graphs, yes. Okay. It's kind of what you're getting there, right? Okay. I'll show you one here. That's you just kind of as intricate as you can get with these things. Go back to GeoGebra, the better of the two graphers. See how I fit that in there? Let's go. I'm showing E. What happens, guys, is that E, your natural number E, becomes a very huge component of the polar system and complex analysis and complex numbers. So I'm going to go E sine to the theta. Okay. It gives me that, but now I'm going to subtract from that 2 cosine of 4 theta plus sine of theta minus pi over 2. I'm going to divide that by 12. I'm going to raise that to the 5th power. And get your butterfly, right? Okay. And you can start, you can start manipulating these things and kind of messing around. Let's see what happens when I change that 4 to a 5. Okay, looks like that. Not much of a butterfly anymore. But then when I go back to that, okay, it looks more symmetric now. All right, so you can start to see some different types of curves that are created, and hopefully and I don't even know if it's possible to change that thing in X and Y's. That would be, it'd probably be a very difficult task. If I wanted a machine, maybe something that was robotic, to move in that curve, it would be so much easier to program my computer with that polar curve, that polar equation, than it would with the X and Y, the rectangular system. Does that make sense? You guys know what a CNC router is? Okay. A CNC. Now I don't know if this is what a CNC or how a CNC router is programmed. Okay. But you can start to maybe look and recognize maybe a benefit of having polar coordinates, and maybe a router like this would be programmed this way. Let's see if you just get an image. All right, so let's use the one I used last class. All right, so a router is just a kind of it's a milling machine. Either mills wood, metal, whatever you need to. Okay, it cuts out an image, right? Okay, routers a lot of times, like woodworkers will use them to curve over edges of wood to smooth them out, or create joinery or something like that, but you can use them to make designs, okay? That hard, and so I have to program my computer somehow, right? And if you're in like, computer-aided drawing and stuff like that, you'll have programs that will allow you to kind of create the picture that you want the router to create, okay? And it'll move in that picture. But when you make that picture, we have to ask, is the software taking the coordinates that I'm putting in and the information I'm putting in as a picture, and I'm dragging points around. It's kind of like maybe a GeoGebra that you would do that in. And then it converts that information into movements for my router. The question is the router and the computer attached to that, taking my input information and converting it into polar coordinates to allow my router to move a little bit more efficiently than just left and right, up and down movements. Does that make sense? Just rectangular coordinates, that thing might look kind of choppy. But it might leave it in rectangular coordinates. I don't know, but that you could see maybe a technological purpose of having polar coordinates, okay, and being able to deal with polar equations and graphs. There were a couple questions, so that's just kind of giving you a visual of some of the things that we can do with polar graphs. Obviously, just skimming the surface of some of this stuff, but there are a couple questions at the end of your homework assignment that I know people struggle with because we haven't got to them yet. They were things like r equals 2 plus 2 cosine theta, and they want you to turn that into rectangular coordinates, a rectangular equation. So when I change it into rectangular, there's no r's left, there's no thetas left. All I'm left with are x's and y's. Okay? And it's an algebra task. It's a substitution process, really, and then altering it to whatever format you want once you get that algebra converted over to x's and y's. So this is how we go about doing this. Now, we know that r equals 2 plus 2 cosine theta is going to be that cardioid. We already dealt with that. I want to change that so it's in x's and y's, and when I graph it in regards to x's and y's, I get the same exact shape. So this is how we go about doing this. It can be messy at times, depending on what you start with, okay? But the three components that we're going to use and variations of these three components are the fact that every time you see an r cosine theta, and it has to be r is r. It's not like a 3 or a 2 or something like this. So this is not r cosine theta. That's 2 cosine theta. Does that make sense? And in the past, people think that r is just an arbitrary constant. It's not. It's r. Okay? But we know r cosine theta should be x. Okay? That's what we talked about when we converted from polar points to rectangular points and rectangular points to polar, right? Okay, is that the x value of rectangular coordinates is equal to r cosine theta. So then the y coordinates are r sine theta, right? So that's all we're doing. Okay, to go from one format of an equation to another, from polar to rectangular, or eventually rectangular to polar, that's all you have to do. Is everywhere you see an r cosine theta, you place it with x. Everywhere you see an r sine theta, you place it with y. However, there's going to be times that r is just by itself. Well, don't we know that r is equal to the square root of x squared plus y squared? Okay? Those are the three things that we need. Now, we might also need the variations of them. For instance, we'll probably use this maybe even a little bit more than the r one. R squared is x squared plus y squared, right? Would you guys agree that cosine is just x over r? And that sine is y over r? And those things are those came from chapter 5. We knew that information. Okay, that's obvious. And that's really where r cosine theta equals x comes from. We knew that from chapter 5, which we knew that information from third quarter of geometry in the 10th grade. Okay, so we're going to take that information, those things on the right, those substitutions, and see what we can do over here. Okay. Now, when we do this, like I said, we like to use that one. Okay. If we can. Okay. So sometimes that takes precedence over maybe using this one. So I don't have an r squared in here, but is it okay to multiply both sides of the equation by anything you want to? Just multiply the left-hand side by r. Does that give you r squared then? If I multiply the right-hand side by r, remember this would be distributing, so I get 2r plus then 2r cosine theta. Well, that's nice, because what's r cosine theta? It's x. Okay. What was r squared? X squared plus y squared. Okay. What was r? Square root of x squared plus y squared, right? Let's go ahead and plug all that stuff in. R squared is x squared plus y squared equals 2 times the square root of x squared plus y squared. And then we have a plus 2, and then r cosine theta is x. Would you guys agree that that green equation is pretty ugly looking? This blue equation, much nicer, right? Okay, and that's kind of the trade-off. That's, learn your polar stuff so that you can deal with a lot less complex looking graphs, okay, or equations, I guess, okay? But we do have the ability with either GeoGebra or Desmos, or, there's other online calculators that you can look at, or online graphing tools that you could use. But this is referred to as an implicit grapher, okay? Meaning that x's and y's do not need to be solved for in order to graph, okay? Desmos is the same way. Your TI-83 or 84 is explicit. Your TI-83 or 84 says you have to have y equals, don't you? Can you envision how difficult this thing would be to get y isolated by itself to graph on my TI-83 or 84? Okay. If you've done it, I know Mrs. Cole is used to kind of walk through this on the TI-8384 in her courses. But if I had like x squared plus y squared is equal to 9, and I want to graph that circle, you guys remember ever taking like y squared is equal to 9 minus x squared? We square root that, we get y equals plus or minus square root of 9 minus x squared. So now I've solved for y1 to be the positive version of this, and then y2 to be the negative version of that. If I graph both those on my TI-8384, I would get the entire circle, right? Okay. I think that might be a very difficult process down there. Okay. So that's the nice thing about having, at our fingertips, the technology that we have with GeoGebra or Desmos, is that I can just type in x squared. X squared plus y squared equals 2 times the square root of x squared plus y squared plus 2x. And did that give me the same cardioid? Okay. Now it's not. Wish GeoGebra would take that and rewrite that as the root, but whatever, doesn't matter. But you see that now in terms of x and the y's, we have the exact same graph that we had when we had 2 plus 2 cosine theta. Okay. Which one would you kind of like to deal with on a more regular basis? Hopefully, the answer to that is this one here in comparison to that one. Okay. Does that make sense? So some of your questions at the end of this assignment were of that. Okay. They were take something like, and this, the reason I'm talking about this is one of your questions on the final exam in this class. Take something like r equals, let's just go 5 sine of theta and graph that, okay? So the question will be take 5 sine theta. It'll say rewrite in rectangular form or as a rectangular equation and then graph. Well, what does this thing look like? A circle. And actually, just to make things a little bit easier, because the midpoint or the center of that circle is going to be kind of nasty, let's make it 6 instead of 7 or 5. Okay? So we got that thing. I want to take this and rewrite r equals 6 sine of theta. I want to rewrite that so that it's in rectangular form. So it's got x's and y's. Okay? So the thing we're going to do, just like the last one, is that we're going to try to generate an r squared here. Well, if I generate an r squared, this thing's going to be multiply the left-hand side by r, multiply the right-hand side by r. So when I do that, I'm going to put the r in a convenient spot. It gives me that, right? What is r sine theta equivalent to? Okay, it's equal to y. So I get x squared plus y squared on the left, and I get 6y on the right, correct? That is your equation of a circle. If you remember, our equation for a circle is always, of our conic sections, it's when x squared plus y squared were being added together and the coefficients for those things were the same. Okay. Otherwise, if they weren't added together, if they're subtracted, we get a hyperbola. If their coefficients are different, we get an ellipse. Okay. But that might not be useful for us in that version to graph it, okay? Because I don't see what my center is, and I don't see what my radius is if I want to graph that, okay? So this is how we do this, and we did this in geometry a little bit. We did it in Algebra 2, and we did it at the beginning of this year in college algebra, so hopefully this is something that we can do without a whole lot of instruction. But we're going to rewrite this thing so that I set it up to complete the square on both the x's and the y's, so I can put this thing into center radius format. There are no terms that group with the x's, so I don't have to complete the square there, but I do have to complete the square here with my y's. So I take half that number and square that, and it gives me 9, right? Add 9 there, and we'll come over here and add 9 there. Add 9 to the left, you gotta add 9 to the right. So now the reason we complete the square is because now that just created a perfect trinomial, which means that it's that can be written as a binomial squared. That 3 right there is always half of that number there. And now hopefully you can tell me that the center is located at 0, 3. Okay, and the radius is located or has a radius of 3 units. Because remember, we're always trying to put this thing back into x minus h squared plus y minus k. Quantity squared equals r squared, where the center is h comma k, and the radius is just r. Would our circle over there on the right abide by that? Would it have a center at 0, 3? And would it have a radius of 3? And if I'm not positive with that, I could, type this in as x squared plus y minus 3 squared equals 9. And you see then again that is indeed the same circle as 6 sine theta. Okay. We might come back and actually show like that is a very nice, concise equation, 6 sine theta. There are even a couple formulas. If we have time, I'll introduce them to you. A guy named Leonard Euler, we've talked about him before in geometry. He did a lot of work with polar coordinates, complex analysis, dealing with complex numbers and stuff like that. And there is an even kind of nicer way of writing this curve. Okay. Just do a couple more examples of that, and I'm actually going to bounce to the WebAssign assignment. They were towards the end. This one here, question 32. R cosine theta equals 9. R cosine theta equals 9. Hopefully, we look at that. What question was it? Okay. R cosine theta equals 9. Well, isn't that x right away? Make that direct substitution. I get x equals 9. If you're questioning whether you're doing this stuff right, graph it. Come over here and say, now, this is the thing with, and I don't mess with Desmos, I'm not sure. But if I go R times cosine theta equals 9, GeoGebra thinks R is some constant multiplier, okay? So I actually, if I'm going to graph these things in polar form on GeoGebra, I actually have to isolate my R, okay? So it's almost like an explicit graph for polar form here. If I graph that, okay, come over here, does that look like the line x equals 9 right there? Okay. In Desmos, let me just check real quick, see what that does. R cosine theta equals 9. Did it do anything? Yep, it graphed it. So maybe Desmos wins there. Okay. 2 for 2. Well, I mean, today. All right, so that one hopefully was not too difficult. Here's one. R equals 8 sine theta. Whenever you have a coefficient and then sine of theta, it's a circle, and it's going to be a circle on let me just graph here before I say anything else. Sine. All right, so it's a circle that is tangent to the x-axis, right? Okay. Because it's sine, it's symmetric with the y-axis. If it was cosine, you see the relationship there, right? Okay. Simply put, it's just tangent to the y-axis now, symmetric with the x-axis. If I start making, multiples of a -1 here, it flips over to the other side of the axis, but it's the same general thing, right? Does that make sense? Okay. Because when I change that, that negative, okay, is going to create that reflection across the y-axis for us when we change to x's and y's. So 33 and 34 are of those. Now, those would be two really good questions to kind of focus on and remember how to do, because, like I said, they're worth about 10 to 15 points on the final exam. And you're going to ask you to graph it, so you're going to want to put it in this form. I think WebAssign will accept it in the kind of the expanded conic section form, but this form here is going to be better for you on the final. This one here, this one's kind of ugly. It says convert the polar equation to rectangular coordinates. You've got 9 plus cosine theta. So R equals 9 plus cosine theta. And I believe this thing is going to be a limousin. No, sorry. Yeah, I think it's a limousin with a dimple, I think, but it's a very shallow dimple, and it kind of looks almost circular when you graph this. But we should know that this is not circular form here. How do we go about doing this? Well, again, we want to use our substitutions. So I want to generate an r squared. So I'll multiply both sides by r. So when I do that now, I do have r squared, which is x squared plus y squared. I now have 9r. Well, r, we know to be this, right? And those parentheses aren't they're not wrong, but maybe they're not necessary. And now what's r cosine theta? X. Now that doesn't look like what we've got going on here, okay? Because we don't have a square root up here, right? I'm pretty certain that if you type this in, you're going to be fine. But the reason they got a square root up there, subtract my x from both sides, so get that thing to the other side. And now what do they do to get rid of the square root? Square everything. So square the left-hand side, and square the right-hand side. Okay. And if you were just to check yourself, I would graph that first, and then graph that, and see if they overlap each other. And that tells you that they're the same. Okay. One last one looks like this. And you could probably start multiplying both sides by r and all that kind of stuff. But just like anything else, if we got fractions, then it's really nice to get rid of fractions as soon as possible. So can I multiply both sides by denominator here? And look what happens when I do that. When I distribute that r3, gives me r sine theta minus r cosine theta equals 9, right? What's r sine theta? Y. What's r cosine theta? X. Y minus x equals 9. Okay? So that's, 9 divided by sine theta minus cosine theta is a linear equation in polar form. Is that okay? Many of you had expressed that you had issues or concerns with some of the questions on the assignment. That's why I extended it until tomorrow. Hopefully that alleviates some of those. Again, if you got questions about anything, please don't hesitate to ask. Tomorrow, remind me if I forget, but everyone has completed the exam finally, Chapter 7 test. So I will pass those back tomorrow. You guys can keep them. So remind me that if I forget to give them to you, because I probably will. So